Okay, let's continue our discussion. So, in this video, we are going to discuss about gravitational potential energy. But before that, let me briefly describe what do we mean by potential energy. So, potential energy is the energy possessed by a body or a system by virtue of its position or by virtue of its configuration. So, we have already seen such a thing in case of a spring mass system. So let's say here we have a spring mass system. This is a spring attached with a block of mass m, and this is its natural length. Let's say here this spring is neither compressed nor elongated. Okay, now if an external force is acting on this block and it displaces this block from here to a new position, let's say this is at x equals to x. So this displacement is x. So there will be elongation in the spring, and due to this new configuration there will be potential energy. And if we are choosing this neutral or natural length here at this position, if we are choosing potential energy to be 0, so at the new position Vx will be kx square by 2. We have seen such a thing already. And work done, what about work done by the spring force? So we already know it is minus kx square by 2, and we can see the potential energy is the rise in potential energy is the negative of work done by this spring force. So we can write here the rise in potential energy here change, but especially I am saying rise in potential energy. There will be increase in potential energy, and this increase will be equal to the work done by the conservative force. So negative of work done by the conservative force. Here the conservative force is the spring force, which is acting against its motion or its displacement. So let me write it, work done by conservative force. Okay, so this is general thing. This is going to happen in other cases too. Like in case of gravitational potential energy, there will be rise in potential energy, and it will be equal to the negative of work done by the gravitational force. In the same way, it is also applicable to electrostatic potential energy, which we are going to see later. But for now, I am going to continue for gravitational potential energy. Okay, before that, let me describe one more thing here. This thing you might have already seen, that if this is Earth and let's say on its surface, okay, let me do one thing here. Okay, so this is the Earth, and if there is a body, this is surface, let's say, and if there is a body of mass small m, let's say, and this body has been raised to a height h from its surface, we say the potential energy in this body will be mgh, and more precisely the mass and this the Earth and this body, this system has potential energy gain of mgh. So in this particular case, we have took few things into consideration. First of all, this h is much less than the radius of the Earth, so that the consequence of taking this thing is giving us, we can consider this gravitational force on this body to be constant. Okay, so in this particular case, and one more thing is here, we have chosen this thing on the surface of the Earth. We have chosen reference point for our potential energy. That is, at this point, we have chosen potential energy to be 0. Now, in reality, this gravitational force is not constant, but it varies with distance. So, I am going to generalize this situation now. So, let's say here we have a body of mass capital M. Let's say here we have a body of mass capital M. Okay, and then this is its center. From its center, let's say we have drawn line, and here we have a body of mass small m, and this body is being moved from point, let's say this is point A, to a new point, let's say this is point B. So here we have changed its configuration, means the configuration of this system where we have two bodies. So there will be change in potential energy here, and that change we can obtain. So if there is a force acting on this body, which is bringing this body from this point to this point, an external force, you can say. At the same time, there will be acting gravitational force on this body, and this gravitational force is along this line directed towards the center of this bigger body. So let's say this is gravitational force. Simply I am writing F. Okay. So if this body is being moved from point A to point B, there will be some work done by this gravitational force also. And we know this force is varying with distance. And we know its relation with distance. F is proportional to 1 by r square. Okay. So now we can say what is the change in potential energy in this case. So for that we have to check what is the work done by this gravitational force, and then we can take negative of that work done, so that will be the rise in potential energy. So but this is varying with position, so we can't directly do force into displacement to get work done by this force. What we can do, we can take a random position here. Let's say this is at r, and then this body is being moved slightly, and this displacement is, let's say, dr. Now we are choosing this direction to be positive, and any vector along this direction we are going to choose negative. This is a kind of one dimensional problem for timing. So what we have now, we have gravitational force, and we can write g m by r square if this body is at this point. So the gravitational force acting on this body, let's say this is F, is g m r square, and we can write unit vector here. So this is along negative r cap. Now, what about dr, small displacement? So a small displacement vector will be dr and along positive r cap. Now, what about the work done? So small work done by this gravitational force is F dot dr, and this will be minus g m by r square dr. Look, r cap minus r cap dot r cap. So this will be minus, and then it will be r cap is unit vector, so its unit is going to be 1 only. So we can write r cap dot r cap will be minus 1. R dot r will be 1 only, and then because magnitude of unit vector is 1, so and here we have minus sign. Okay. Now what we can do, this is for this small displacement, means from here to here, from here to here. If we want to know what is the work done by this gravitational force while body is being moved from point A to point B, we have to do integration here. So what we can do, work done by the gravitational force if the body is being moved from point A to point B, we can write integration of this thing from point A to point B, or we can write, let's say at point A its position is r1, and at point B its position is r2. So from here to here, let's say it is r1, and from here to here, let's say it is r2. Okay, now we can do here. So this will be minus g m by r square dr, and r1 to r2, and this will be we can take g m outside because this is constant. So g capital M small m, and then we will have r square can be written as r to the power minus 2 dr, and then we can write from r1 to r2, and then we will have work done minus g capital M small m, and here we can write r minus 2 plus 1 divided by minus 2 plus 1, and from r1 to r2, and this will be minus g mm, and this will be minus g mm 1 by r, negative of this thing. So r1 to r2. So we can write here minus g, and I can take it out. So this will be plus g m small m 1 by r2 minus 1 by r1. This is what work done by the gravitational force. while this body is being moved from point A to point B. Okay, so let me write it again. Work done equals to Gmm 1 by R2 minus 1 by R1. This is what. So this is the change in potential energy actually. This is the change in potential energy when the body is being moved from R1 to R2. And if we take negative of this thing, this will be the rise in potential energy, means the value by which the potential energy has been increased. So let it be as it is. So change in potential energy can be given as this. Okay, now we can take reference point and then we can say what is the potential energy at particular position with that reference point. So let's take our reference point at infinity, and at infinity we are going to choose potential energy to be 0, and this will be consistent because if we are choosing this tending to infinity, 1 by R2 is tending to 0. Okay, in this case we can say the potential energy at point where R1, let's say at distance R1 or at position R1 more precisely, this will be minus Gm m by R1. And look, R1 is an arbitrary point. So we can say in general, the potential energy of this system when this small mass m is at R, we can say the potential energy will be Gm small m by R. In general, we can say it. Okay. Mind it, this is our consideration when we have chosen potential energy to be 0 at infinity, means infinity is our reference point. Okay, so one more thing, infinity is not a particular point, this is just a mathematical representation. Okay, so let me rewrite the situation here. So if we have a body here of mass capital M, and from its center, let's say this is symmetric body, so we can consider its mass to be at center, and there is another body and the center to center distance is r, and this body has mass m. So for this configuration we can say the potential energy of this system is minus G m into m by r. This is what we have obtained from the derivation above. Okay, now we can move for multi-particle system. So here we have chosen only two. What about there are more bodies or there are more particles or masses are there? So in that case, okay, let me bring it potential energy of multi-particle system. So what will happen? Let's say here we have a body of mass m1 and another body here is brought, let's say m2, and this is r21, let's say this position. And then the potential energy of this system will be minus G m1 m2 by r21 square. Sorry, minus r21. Okay. Now, what about we are bringing another body, let's say of mass m3 here. So, if we are choosing this configuration, so there will be potential energy due to its configuration, and we can say now it is experiencing two different gravitational forces, one due to this body, another due to this second body. So this third body is experiencing two different gravitational forces, and due to those two different gravitational forces, we can say that it has to deal with two different potentials here. So potential energy of the system now will be, look, if we have brought this second body here, then potential energy of the system is this much. Now we have three bodies. So the potential energy will be minus G m1 m2 by r21 for this one. So this is for two bodies, this is for three bodies, and then this body is also being brought here. So this will be G m1 m3 by r31 here, let's say this is R31, and let's say this is R32, and this is R31, and there will be another plus G M2 M3 now by R32. This is what. So what is happening? There is one body which has been brought from infinity to this point. So there is no gravitational force acting on this body, and then there will be no work done against the gravitational force. So there won't be any change in potential energy. But if this body is here, and now we are bringing this body from infinity to this point, there will be gravitational force acting on this body M2, and due to that gravitational force, there will be potential energy, change in potential energy, more precisely this much, and we have chosen potential energy at infinity to be 0. So in that case, potential energy at this point will be given as this expression. Now if we are bringing the third body in the system, now the system has this potential energy due to this body already here, and then by bringing this body here, we have changed the configuration again, and now it has experiencing two different gravitational forces, one for this here and another for this body. So it has to deal with two different gravitational potential energies here. So this is for M1, M3 system, that is, this is M3 due to this body, and it is also experiencing gravitational force due to this body. So there will be another term for gravitational potential energy due to this body and this body. So now the system has gravitational potential energy as this. So you can generalize the situation. You can take n number of such masses or particles, and then you can continue this series here. So in this way, okay, let me take an example, then it will be more clear to you. So if there is example given here, let me check it out. Yes, here we have an example. So what is it saying? Find the potential energy of a system of four particles placed at the vertices of a square of side L. Okay, the side of the square is L. So let's say this is L. So this will be L also, and this is also L, this is also L. Okay, let me write here. This is A, this is B, this is C, and this is D. Now we have to place four uh, spheres here. So let me bring. So for the first sphere, if I am bringing to point A, there is no gravitational force acting on this sphere, and then there won't be any change in potential energy of the system. Okay. Now what about the second one? If I am bringing the second sphere here, let's say here, now this sphere is experiencing gravitational force due to this sphere. So there will be change in potential energy in this particular case. So if I'm bringing the second sphere, let's say the second sphere, the potential energy of this system is now minus G, and let's say all has same mass. So potential four particles placed at, okay, let's say masses are n, m, and all m. So this will be G m into m by r square. R is here L. So this will be not square, only L. So minus G m into L. So we can write minus G m square by L. Now, what about bringing the third one? So if we are bringing the third one, the new potential energy will be minus G m square by L. This is already here. Now, by bringing this third sphere, we have changed the configuration again, and then we will have, look, for this body, it is at distance L, so it will be minus G m square by L, as we have discussed this thing. So this is very identical to this situation. But for this body, we have to find out what is the distance here. So you can do it. L square plus L square will be the AC square here. So this is a perpendicular, let's say this is base. So base square plus perpendicular square equals to hypotenuse square. So this will be uh, L into under root 2. So here we will have minus G m square L into root 2. Okay. What about the fourth sphere? If I am bringing this fourth sphere here, now be careful about this. Now it has to deal with this sphere also, and this sphere, and this sphere also. So it has two distances L and L from these two spheres. So the new potential energy will be of the system. This will be minus G m square by L plus minus G m square by L plus minus G m square by L root 2. This was already here for the three spheres. Now I am adding for this one. So, okay, this will be, look here, minus G m square by L once again, and due to this sphere, it will be minus G m square by L, and this is also L into square root of 2, this length dv will be, so we can write here minus G m square by L into root 2. Now you can rearrange these things, and this is 4 times of this term and 2 times of this term. So you can rearrange and you can obtain what is the potential energy of this particular system. So, okay, let me try it. So this will be minus 4 G m square by L, and then minus twice of this thing. So minus 2 G m square by L into root 2. Or you can do further calculations to arrive at simpler term. Okay, so this is all for this video. And yes, before ending this video, let me introduce one more thing here. We have till now discussed gravitational potential energy. Now I am going to introduce one more term here, and this is gravitational potential. Gravitational potential. Okay. So if there is a body, let's say this is a body of mass capital M, and from its center there is another body at distance r, and it has mass small m, we have seen that potential energy for this configuration is minus G capital M small m by r. Now I want to know, if there is no small m mass here, still there will be gravitational field around this body, and due to that gravitational field there will be gravitational potential, and this gravitational potential we are going to write as, let's say, u r, and we can define the potential energy per unit mass at distance r. If there is no mass here, still there will be gravitational potential, because if this body is here and you are bringing another body, there will be change in potential energy. So this body is here creating gravitational field around itself, and due to that gravitational field there will be gravitational potential, because if you bring any body of some mass into that field, there will be change in potential energy of the system. So this gravitational potential I am going to describe as, gravitational potential is gravitational potential energy per unit mass at point r. So we can write u r for this mass m, capital M, will be minus G into capital M by R. This is gravitational field, and if we are bringing this mass small m here, there will be gravitational potential energy in the system, and that potential energy we have seen already here. Okay, this is what gravitational potential. Now, one more thing I am going to introduce, that is gravitational intensity. So, like gravitational potential, which is gravitational potential energy per unit mass. Okay, so in the same way, I'm going to say gravitational intensity, and gravitational intensity is gravitational force per unit mass. So I'm writing, let's say at this point there will be gravitational force acting on this mass m, and this gravitational force, let's say, is F r. So we can write gravitational intensity at this point, or simply gravitational field intensity, will be this much, and this is G m by r square in magnitude, or if you are taking direction, then you have to be specified about this thing. This is positive, then this will be negative one. So you can write minus r cap, because force is directed along this thing, along this line. So along this, towards the center of this bigger cone. Okay. So this force is along, let's say F, this is along minus r cap.